Welcome to this complete machine learning video. Today I will walk through my actual diabetes prediction notebook, every single line of code, plus explain all the theory behind it, including the sigmoid function, the area under the ROC curve, confusion matrix, precision, recall, F1 score, and more. This is a full end-to-end supervised machine learning walkthrough. Let us begin. What is logistic regression? It is a supervised machine learning algorithm for binary classification. Output is 0 or 1. In our case, 0 means no diabetes and 1 means diabetes. The key is the sigmoid function, which converts any real number into a probability between 0 and 1. The z-score is the weighted sum of all input features. High z means high probability of diabetes. Here is the live sigmoid curve. The x-axis is z, the weighted sum of patient features. The y-axis is the predicted probability of diabetes. Notice the beautiful S-shape. At z equals 0, probability is exactly 0.5, that is our decision boundary. Drag the slider to change the z value and watch the probability update. Try dragging to a high positive value, notice the probability shoots up towards 1, meaning diabetic. Now my actual code. Step 1. I import NumPy as NP and Pandas as PD, filter warnings to keep the notebook clean, then load the diabetes CSV from Google Colab using Pandas read_CSV. I call head, to preview 5 rows, shape gives me 768 rows and 9 columns, and is null.sum confirms 0 missing values. This dataset is perfectly clean. Steps 2 and 3. Feature target separation and train test split. X contains all columns except outcome, our 8 clinical features. Y contains only the outcome column, 0 or 1. Then we split, 75% goes to training and 25% to testing using train_test_split with random_state 0 for reproducibility. X_train is 576 rows, X_test is 192 rows. Step 4. Training. I create model 1 as a logistic regression instance, then call model1.fit with x_train and y_train. During fit, the model runs gradient descent hundreds of times, adjusting the weights for all 8 features to minimize the log loss. After training, model1.predict on x_test gives an array of 192 predicted values, each is either 0 or 1. These predictions are compared to y_test to evaluate performance. Step 5. Evaluation. My code uses accuracy_score, which gives 77.6%. But accuracy alone is not enough, especially for imbalanced datasets. Accuracy just counts correct predictions divided by total predictions. If we had 90% non-diabetic patients, a model that always predicts 0 would get 90% accuracy without learning anything. That is why we need the confusion matrix and other metrics. The confusion matrix is the most detailed way to understand your model. It breaks predictions into 4 cells. True positive, model predicted diabetic and patient is diabetic, correct. True negative, predicted not diabetic and patient is not diabetic, correct. False positive, predicted diabetic but patient is not, wrong, a false alarm. False negative, predicted not diabetic but patient is diabetic, the most dangerous error in medicine. We missed a sick patient. Now precision and recall, 2 of the most important metrics in medical AI. Precision asks, of all the patients I predicted as diabetic, how many actually were diabetic? Our precision is 42 divided by 42 plus 21, which is 66.7%. Recall asks, of all the actual diabetic patients, how many did I correctly identify? Our recall is 42 divided by 42 plus 22, which is 65.6%. In medicine, recall is more critical. We want to catch as many diabetic patients as possible. The F1 score is the harmonic mean of precision and recall. It balances both into a single number. The formula is 2 times precision times recall divided by precision plus recall. Our F1 score is about 66.1%. The F1 score is especially useful for imbalanced datasets like ours. A perfect F1 score is 1.0. The closer to 1, the better. The harmonic mean punishes extreme imbalances. If either precision or recall is very low, F1 will be low even if the other is high. This slide explains how changing the decision threshold changes precision and recall. By default, logistic regression uses 0.5 as the threshold. If probability is above 0.5, predict diabetic. But we can lower this to 0.3. At threshold 0.3, we catch more diabetic patients, recall goes up, but we also get more false alarms, precision goes down. Drag the threshold slider to see this trade-off live. The ROC curve stands for Receiver Operating Characteristic Curve. It is one of the most powerful evaluation tools in machine learning. The x-axis shows false positive rate and the y-axis shows true positive rate, which is the same as recall. Each point on the curve corresponds to a different decision threshold. A perfect model goes to the top left corner, 100% true positive rate with 0% false positives. A random model follows the diagonal line. The area under the curve, AUC, measures overall model quality regardless of threshold. Here is the ROC curve for our diabetes model. The purple curve is our model. It rises steeply towards the top left corner, which is great. The red diagonal dashed line is a random classifier. The shaded area under our curve is the AUC, approximately 0.84. This means our model is much better than random guessing. Even though accuracy is 77.6%, the AUC of 0.84 tells us the model has strong discriminating power between diabetic and non-diabetic patients. After training, we can inspect the coefficients, the weights the model learned. These tell us which features matter most. Diabetes pedigree function has the highest coefficient, meaning family history is a very strong predictor. Glucose is also very high. BMI and pregnancies have positive coefficients. Blood pressure has a near zero coefficient, meaning it barely contributes. The chart shows these weights. Purple bars increase diabetes risk, any negative bar would decrease it. The interactive prediction playground. Adjust all 8 patient sliders and see the model predict diabetes risk in real time. The lower bar chart shows each feature's contribution to the Z-score. Purple bars push towards diabetic, red bars push towards not diabetic. Try glucose above 160 and BMI above 40, watch the risk shoot up. This is exactly how our trained model classifies each of the 192 test patients. Final slide. Let us summarize all our evaluation metrics. Accuracy 77.6%, precision 66.7%, recall 65.6%, F1 score 66.1%, AUC ROC approximately 0.84. The AUC of 0.84 tells us our model is a good classifier even though accuracy and F1 are moderate. Now a quick quiz, then the credits. Thank you for watching.